introduce our next speaker, Peter Lodahl from the Niels Bohr Institute. We'll be talking about coupling of quantum dots to photon crystal waveguides.
Yes, thank you very much, Derek. Yeah, I will be continuing along the lines of the two previous talks. So there's been excellent introduction to what I will be talking about. I will do quantum optics in one-dimensional directional photonic reservoirs. I'm coming from the Niels Bohr Institute, University of Copenhagen, where I'm heading the quantum photonics group. And I'll be, well, the general introduction to what this is about. Hardly have to mention this audience, but we want to construct photonic quantum networks. Of course, we have our heroes from the atomic physics community. We have them in the US and in Europe. And they have been doing cavity QED experiments for years and thinking about wiring up quantum nodes into large-scale quantum networks. And we want to do it all solid state. So it's, again, quantum dots embedded in photonic crystal nanostructures. And I think it's quite exciting times for our field, for our community. I think we have been solving child diseases, curing child diseases for years because, I mean, this is solid state, so one has to worry about decoherence processes, and many solid state systems are not coherent at all. It's embedded in a solid, and this solid will vibrate due to phonons and whatnot. And, I mean, we're really starting to solve these issues, and we have heard beautiful progress along these lines already from Ido and Kai. And so we have been developing puzzle pieces over the years, I would say, and I will discuss some of these puzzle pieces today. And I think we are, as a community, now starting to ask the question, so how do we scale? How do we put these puzzle pieces together into large-scale quantum architectures and do something interesting there? So I'll be talking about efficient single photon sources. I'll also be saying something about nonlinearity, some recent work we have there. Of course, also has been mentioned already for superconducting detectors can be naturally embedded on these structures or incorporated in these structures, so we can do everything on chip. We can do processing of photons, also making photonic circuits for that. We can also have long-range interaction, dipole-dipole interaction, because we can make nice 1D systems. And we can also couple the photons out from the photonic crystal structures by making tapers and coupling into fiber and propagating photons over long distances. And for kind of details of where the field is at the moment, I'll refer you to this review paper that came out in Review Modern Physics just about a month ago. So the outline of the talk is I'll say something about photonic crystal, local light matter interaction of photonic crystals. I'll talk about deterministic and directional single photon emission that we can achieve in these structures. I'll talk about single photon nonlinear optics and say something about quantum information processing and the prospects for quantum information processing based on these systems. So, photonic crystal are these periodic dielectric structures we've heard about. We have two-dimensional photonic crystals made by electron beam lithography and your etching, and we create a 2D structure. We make a membrane, so we remove the sacrificial layer underneath, so we get a 150 nanometer thin gallium arsenide membrane where we have a single layer of quantum dots inside. And so of the cartoon density of states that you would have in such a structure sketched here, there would be a band gap range of frequencies where density of states is strongly suppressed. It's an interesting question, how much, and I'll answer that in a question in a minute, because this is really the name of the game of photonic crystals. You can suppress leakage to all unwanted modes, and then you can enhance the coupling into your cavity or the waveguide. So this is really the secret weapon of photonic crystals. But how much can I control spontaneous emission? How much can I suppress spontaneous emission? Well, that's linked to what's called the local density of states. Its mathematical definition is up here. In Wigner-Weisskopf theory, it's directly proportional to the radiative decay rate. So if I have a quantum emitter, I place it inside the structure, I measure its rate, and it's in the Wigner-Weisskopf approximation, so it's a Markovian light-matter interaction, and this is usually the case unless you are close to band edges and things like that. Well, then you just measure this rate and you can probe the local density of states, but you need to make sure that, you know, there will be non-radiative processes, so you really need to know your emitter very well in order to be able to probe just the radiative part. So we have done quite some extensive works along these lines. I'll not go through the details here, but really, I mean, studying quantum dots in known photonic nanostructures that we can use to really learn how you probe the radiative decay rate. If you measure or calculate the local density of states here, you see the spatial map of the inhibition factor in the bandgap region for an X-oriented dipole and a Y-oriented dipole, and it really promises that you can suppress spontaneous emission by factor up to 160, and it's really at many different spatial positions. And this is because I have a 2D band gap, but I have the membrane, so I have total internal reflection at the gallium arsenide air interface, and this is really sufficiently, this combination is really sufficiently efficient that I can suppress spontaneous emission that much. What doesn't work in experiment, well, those are man-made structures, but there will be fabrication imperfections and so on. So here's, we have actually measured this local density of states by looking at measuring this radiative decay rate of single quantum dots. You are then probing the frequency dependence of the local density of states, and so we are varying the lattice constant of the photonic crystal and therefore getting the frequency map of the local density of states. And the numbers here, it's a logarithmic scale, so you really see suppression of up to a factor of 70 of inhibition of spontaneous emission these structures. So it's, say, within close to a factor of 2 of what theory expects. And this is really good news, because that means that this suppression of leakage to all unwanted modes is really a very, very robust effect. It's spatially robust, it's also spectrally very robust, and it's also robust to fabrication imperfection. So it's really something that is very robust to extend on. So what we can then do is to, of course, introduce waveguides and cavities in these structures. So it's very easy. You leave out a row of holes that creates a photonic crystal waveguide, and then we can embed single quantum dots in these waveguides, and that can be used really as an extremely efficient single photon source. And the figure of merit is the beta factor, the rate of coupling into the waveguide relative to the total emission rate of the quantum dot. It can leak out of the structure due to the coupling to these non-guided modes. But those were the ones that I could suppress very much by the band gap, or this factor of 70 I was talking about. There will also be some kind of non-radiative processes inside the quantum dot. I excite the quantum dot, but it doesn't necessarily emit a single photon. The excitation could go somewhere else. But I can also enhance the coupling into the waveguide mode. That's because these waveguide modes are strongly dispersive. So here you see the dispersion diagram of the photonic band gap structure. You have a band gap region where that's in between those two lines here. And in this band gap, I start to introduce modes. And that's a waveguide modes that are guided along the waveguide, that are propagating modes along the waveguide. But they're very dispersive. So if I calculate the group velocity, the omega decay, well, it will go to 0 ideally here at the frequency at the cutoff of the band gaps of the mode here. So I can slow down light, and thereby I can also enhance the coupling into the mode, because the density of states of this waveguide mode is inversely proportional to the group velocity. However, there's a limit to how well I can do that, because this slowing down of light is very sensitive to fabrication imperfections. So that means in practice what I can do is slowing down light, typical factor of 60 we will see in the lab, maybe up to a factor of 100. But if I calculate then the expected beta factor, so the spatial map of this beta factor, you can see it over here for these realistic slowdown factors of, say, 58, you will see that, well, the expected beta factor is close to ideal. So the numbers are 99.8% efficiency. And it's really spatially robust at many different spatial positions inside the waveguide. So the nanostructure is almost perfect. And even when I'm not using slow light for a group index or slowdown factor of 5, I'll still have a beta factor, expect a beta factor above 98%. And the reason for that is really that I'm very much relying on the suppression of coupling to leaky modes to enhance this beta factor. So to the experimental demonstration of this beta factor, well, what you do is that you're measuring the rate of these quantum dots. So you look for well-coupled quantum dots, and you see quantum dots that decay with rates up to 6 or 7 inverse nanoseconds, and then you're searching for quantum dots that are not well coupled. It's actually not so easy to measure a beta factor very close to 1. But you're looking for the weakest coupled quantum dots, and we see quantum dots that have decay rates that are slower than 0.1 inverse nanoseconds, and then you compare that to the best coupled quantum dots, and then you want to make sure that this is a fair comparison, because you're looking at quantum dots that are sitting at different positions. But actually from their rates and the known local density of states, you can narrow down quite well what spatial position they might sit at. So we can actually, from that, get a lower bound of the beta factor, which is 98.4%, which corresponds to a cooperativity of 62 at least. So this works pretty well. And it's not just one quantum dot that has a high cooperativity and beta factor. Here's the statistics of I think 70 different quantum dots. and you see the beta factor as a function of wavelengths. This is the cutoff of the waveguide mode, and you see, so this is a slow light regime where you have this beta factor of 98%, but it also ranges out far away from the band edge again, because it's spectrally extremely broad, because it doesn't necessarily require the slow light. And here we are comparing two different outcoupling strategies. You can make all these kind of nice gratings, for instance, that couples the light vertically out of structure. You can also make tapers so that you can collect the light from the side of the waveguide, and you can make all kinds of designs here, and those are by now also quite outdated designs. So you can really it's really an impedance matching task to take the light from inside the waveguide and then couple it off chip for efficient detection. It was mentioned in the previous talk also. I mean, this is just an engineering task where if you're sufficiently serious about solving Maxwell's equation, first to engineer a structure that accommodates and propagates the light well out of the structure, and then of course making it come up with a design that you can fabricate and that is tolerant to fabrication imperfections and so on. And we have all kinds of ingenious designs for doing that, something that we're working hard at the moment. So the intrinsic quantum efficiency of beta factors is 98.4%, but of course coupling them off chip is another issue. And there will also be questions about, so once I have excited the quantum dot, how sure can I be that it emits a single photon? Is it really a source that emits a single photon every single time that I excite it? And not necessarily, but this is where, I mean, people in the field really have demonstrated that, well, you can have all kinds of blinking processes. The quantum dot can go dark for a certain period of time if it traps an additional charge, for instance, or a charge escapes from the quantum dot. And you want to avoid these processes if you really want this stream source here that emits a single photon every single time I trigger it. But this can be solved. I think putting gates on the structures has really shown to be a key to doing that. I mean, putting electrical gates, so you're stabilizing the electron hole pair inside the quantum dot, and well, doing resonant excitation. I mean, things like that really have solved these issues. Well, this is just a sort of figure from our review paper explaining these different approaches to 1D nanophotonic systems that are becoming quite popular, and what this workshop is about. Also, we have these photonic crystal waveguides that we're talking about here. We also have dielectric nanowires, pioneered particularly by Jean-Michel Girard in Grenoble, and we also have plasmonic nanowires that have also been proposed here at Harvard. And you can say that photonic nanowires exploit suppression of coupling to radiation modes. Plasmonic nanowires enhance the coupling into the plasmon nanowire in this case. Photonic crystal waveguides do both effects at the same time, so you suppress and you enhance. And this is kind of the status of the numbers for the various systems. But we can do more than, of course, generating single photons, and you can also exploit this very high cooperativity and this high beta factor to do single photon nonlinearity. And this has pretty much been proposed by the audience here, so I hardly have to explain it. If we were talking a lot about it also in the morning session from about superconducting qubits, and it's almost a little bit embarrassing, or certainly a challenge to speak about the optical experiments here after these fantastic results that we have been seeing in the morning. We're not quite there yet, but actually the potential is there, and because the coupling efficiencies, the cooperativities that I'm talking about, is actually pretty good. So the idea is you launch single photons, and a single photon will be reflected with beta squared probability. Unity probability beta is 1, and 2 and higher photon components will have an increased probability to be transmitted. However, it's more than just beta in this case, because this is coherent scattering, so any decoherence processes will reduce the reflectivity coefficient. And here's the expression for how it looks like if I have pure dephasing in the system. So that's just a broadening of the zero phonon line. So that corresponds to very large, very fast dephasing processes. But I can have all kinds of and I do have all kinds of decoherence processes. There can be spectral diffusion, that the line is flickering, going back and forth on slow time scales. It can blink and so on. And this is, as I already mentioned, this is really where there has been very exciting progress, I think, in the field, that people have really started to overcome these decoherence processes. Meta Tatura, for instance, at Cambridge, Richard Warburton in Basel have shown that we can get close to transform limited lines from a single quantum dot. There will always be a little bit of phonon broadening, phonon sidebands. So even at 0 Kelvin, there will be probability to spontaneously emit single photons. So that gives a little bit of phonon sidebands if you zoom in on the lines here. This is at the level of 5%, and we also know what determines that. We can actually control that ideally by controlling the quantum dot, the size of the quantum dot wave function. So spectral diffusion, that is due to charge noise. All charges in the vicinity of the quantum dot roaming around will give rise to spectral diffusion. And this has really been overcome with quantum dots. This is what this works here shows. So we have up to 95% emission in the 0 photon line. People have demonstrated larger than 96% indistinguishable photons. And the tricks are really to put gates on the structures and do resonant excitation to obtain this performance. So here are our first data on the single photon observation of the single photon nonlinearity with a quantum dot in a photonic crystal waveguide. So there we make all these composite photonic crystal structures. We have a quantum dot sitting in a slow light photonic crystal waveguide section in order to have the high beta factor. And then we gradually change the lattice constant so that we go from a slow light section into, well, what we sometimes call a fast light section, where you don't have the high group index. Because this fast light you can better impedance match to a dielectric waveguide, that you can better impedance match to a grating, and that you can couple out with high efficiency. And then we have a transmission type experiment here where we are launching light on this grating, transmitting through the quantum dot, and looking at the transmission from the other grating. And well, these are relative transmission measurements when we are scanning the resonance of the laser through the quantum dot resonance. And we see transmission dips here at the 8% level in this case. Best performance we have seen is about 15%. Limited so far by spectral diffusion, actually, because we don't have gates on these structures yet. This is next generation experiments. So that will mean some jitter will really mean that we don't get the beta squared performance that we ideally could expect in this case. If we measure the transmission here as a function of photon flux, or the power on the sample, so this is for a weak coherent state, we are seeing that the nonlinear behavior here that levels off with a characteristic switching energy that corresponds to less than 1 photon per lifetime of the emitter. So that's a saturation really at the single photon level. And we can also, from these data and also the data I'll be showing on the next slide, we can actually determine the parameters really describing this responsible for this nonlinear response. So it will be the beta factor, it will be the pure dephasing rate, that's the broadening of the 0 photon line, and then it will be the spectral diffusion I was talking about. The spectral diffusion is something you should just get rid of. That's a sort of a trivial decoherence processes. That's just some rubbish in your data, and again these gates should make sure that this is possible. So you have deconvoluted the transmission response without the spectral diffusion. You see that what you could expect would be up to a 40% transmission dip in this case. The beta factor for this particular quantum dot was 88%, and we actually had some residual broadening of the 0 photon line of 0.7 relative to the radiative lifetime, which is the limiting factor in what we are seeing here. I should also point out that, of course, there's a lot of work, we've heard about it already from Edu and also from Guy, of nonlinearities with on cavity polaritons, where you're using the anharmonicity of the Jaynes-Cummings ladder as a nonlinear medium. So Imamoglu's group as well, Pascal Senelar. So what we're using here is the nonlinearity of the quantum dot instead. So we can also measure the photon statistics. So then you should see this this photon sorting going on, that the single photon contribution will be reflected, and 2 and higher photon components will have increased probability to be transmitted. So I should see photon bunching in the transmission, and this is also what we see, although modest 8% effect. This is very sensitive to pure dephasing, it turns out. So observing this photon bunching is highly sensitive. Shows that we are actually quite coherent, even though we don't have electrical gates in these structures. And we see this G2, this bunching disappearing when we're increasing the power on the sample. And again, we have the deconvoluted response here if we overcome the spectral diffusion. Okay, so this was photon nonlinearities. Now I'll tell you about another type of waveguides we have recently studied that we call glide plane waveguides. And this pretty much shows, very much emphasizes the engineering potential of photonic crystals, because it's a highly inhomogeneous structure, and there's all this freedom that you can choose lattice constant, you can choose, design a structure that does interesting things. And here we have designed a structure that gives rise to unidirectional emission. So this can be used for interfacing spins and photons and spin-photon entanglement. And the trick is really to, the waveguides I was talking about before were symmetric around the plane here, around the waveguide plane. So if I there's a mirror symmetry around the waveguide plane. And an outcome of that is that the modes here are primarily linearly polarized. So here you see the electric field, Ex and Ey, linear polarization components of the electric field in the photonic crystal waveguide. If I break this symmetry, I introduce what we call the glide plane symmetry, that you translate the upper half here by half a lattice constant. You change the polarization of the mode. So here we show the projections on a right and left circular polarized basis, so Ex plus I, Ey, and you see that the modes here are primarily circularly polarized. And this has important consequences, because if I then put a circularly polarized emitter inside this photonic crystal waveguide, I place it at a position where the local polarization is also circular, then this emitter will actually emit along just one direction. Because the interaction is D dot E, so if the local electric field matches exactly the circular polarization of this emitter, it will just go along one direction, because from reciprocity, E propagating along one direction and the one going the other direction, it's a complex conjugate of that. So that means if I have perfect interaction along one direction, it's orthogonal, and therefore the interaction is zero along the other direction. So that's the idea about this chiral photon emission. If I put a sigma plus polarized emitter and it matches exactly the same polarization, circular polarization in the waveguide, then I can get this emitter to decay to the right, say, and have no emission to the left, and vice versa for sigma minus polarized emitter. So this is a numerical simulation of this effect, and if we calculate, so how efficient is this, we can define the directional beta factor. What's the probability that my emitter emits a photon in the direction that I'm interested in, that this emits to the right, as opposed to emitting to the left or radiating out of the structure due to coupling to radiation mode. That's a directional beta factor. Well, the numbers here are up to 98%. So I could get a directionality, a deterministic directional emission, ideally. And I think actually we should be able to go to 100%. There's no reason why, I cannot engineer this to go very close to 100%. I think that's just an engineering challenge. So the experimental demonstration of this effect is that you see here again a composite structure. You have a glide plane photonic crystal waveguide section that you see here where we've broken this mirror symmetry, and then we actually again adiabatically change this mode so that you can to a regular photonic crystal waveguide mode out here that you can couple out in a dielectric waveguide, and you can collect light from two gratings here. Then we identified single quantum dot lines, as you can see here. It's quantum dot line A and quantum dot B, and then we're putting a magnetic field on these quantum dots to split them and induce in-plane circular polarization. And then you see for line B here, for instance, red means I'm collecting it from the left grading, blue means I'm collecting it from the right grading, that the B plus, sigma plus polarized transition emits almost only to the left. I only collect a little bit to the right, the blue curve here, and vice versa for the B minus. And similar behavior for A plus, and I can then extract the directionality of this single photon emission here. You see the directionality as a function of magnetic field, and you see the numbers here up to about 90% directionality for line B and somewhere smaller for line A. We think this is actually limited by the way that we do this experiment. We did non-resonant excitation, so you see there's a little bit of grass in the spectra here. That means I cannot, have I don't see the lines going all the way to 0. So I think in reality the directionality could be much higher. And we do some G2 measurements also here to show that this is really single photon directional emission. I should point out there's also related work from a group in Sheffield where they're using crossed dielectric waveguides to observe such a directional emission. So those are examples of unidirectional photonic reservoirs that are becoming quite popular. These photonic crystal glide plane waveguides are one example. There's also all the beautiful work in Arno Rauschenbeutel's group, and we'll hear about that tomorrow. So they are trapping atoms in the vicinity of tapered fibers, and there they see also that these evanescent modes that you have there have a strong longitudinal component, and that gives rise to this directional behavior as well. And there's of course also here at Harvard, Michel Lukin's group, trapping atoms in the vicinity of photonic crystal cavities, and similar type of effects would be expected there as well. It's another way of making one-sided system is of course just to take a one-sided cavity. But you might also exploit this longitudinal component of the electric field, which we also call spin-orbit coupling of light to induce directionality. And you can do some funny things with such a unidirectional photonic reservoir. You can start to create non-reciprocal photonic devices, integrated photonic devices. Because if I make a Mach center interferometer as indicated here, and I have a small glide plane waveguide section in one of the arms, then if I send in two pulses, two photons, one is resonant with a transition that can only emit to the left, and the other is non-resonant, well, then the transmission coefficient for this situation is 1 minus 2 beta directional. A single photon will not be reflected like we're used to due to this destructive interference between scattered light and the illuminating light, because this scatter this direction is suppressed. So it can only go forward, and it will acquire a pi phase shift in doing that. So that means if a blue photon comes in, it requires a pi phase shift, and it will go to, say, from down to down, while the red photon that is not resonant will go from down to up because of this pi phase shift that the blue photon acquires. That means if I go backward, the red photon is still non-resonant, so it will go from up to down, but the blue photon will also go from down to up, because that's not interacting with the emitter anymore, because its d dot e is 0 as opposed to being optimum when propagating forward. So I'll actually have non-reciprocal behavior. The blue photon does end up in a different port than the non-interacting photon. And well, you can think about making gates like this, and there's not much new, I think, in this gate. It's a Duan Kimball idea that we also heard from Edo about. But you can think of making a fully deterministic on-chip photon C0 gate based on this. And I think the new thing for an experimentalist like me would be that now I can really picture how I would get the photons in, and what resources do I need in order to do that fully deterministically. I can start to draw it and say, okay, I need 3 input ports here, and I can send the control photon and target photon from 2 different directions. I don't need to split it up and do things because of directionality. I do need to be able to also interact deterministically with the control photon. So that means that I need to be able to switch this Mach center interferometer, so that I go from, say, sending the photon deterministically in here to having 50-50 beam splitters. So one resource that we will need is also adjustable or tunable beam splitters, and we are envisioning doing that with electromechanical control of photonic waveguides. And I'll not go through it here, but this is kind of the layout of this deterministic photon-photon gate. How much time do I have?
5 minutes.
Okay. So I'll say a little bit about photon sorting, because so this gate requires that we are applying pulses we're controlling the spins inside the quantum dot, and we are preparing coherent superposition like what Ido was talking about. It would of course be nice if I could do something just with passively scattering photons on a two-level system, because that's extremely easy. I just use the quantum dot and the nonlinearity of the quantum dot as a passive scatterer. And this was an idea, actually continuation of extension of proposals of Anders and Misha of trying to do photon sorting and trying to do it efficiently. This was something we did together with Tim Ralph at UQ in Australia, that if I scatter 1 and 2 photons, I scatter superposition of 1 of 2 photons, I might be able to separate those 2 components from each other if I do it in a proper way. Thing is that I cannot just, with a single scatter, I cannot just get the 1 photon to be reflected and the 2 photons to be reflected perfectly, but I can do something else. If I choose the pulse width of the mode properly, I can, in a single scattering event, create a situation where the 1 and 2 photon components are in orthogonal spectral and temporal modes. I will distort the pulse by scattering, but I'm distorting it in such a way that 1 and 2 photons are exactly in orthogonal spectral temporal mode. So that means I should be able to distinguish them or to take them apart. But I need something more than just passive filtering, because they are not. It's not just spectrally that they don't overlap. It's the spectral temporal mode that is orthogonal. But I can do such a separation by, for instance, some frequency generation, and there's a group in Paderborn in Germany that are really experts in doing that. That's single photon. So by level, so with high efficiency, with high efficiency. So by controlling the spectral temporal mode of the pump, you can spectrally transduce the spectral temporal mode that you're interested in. So I could transduce a 1 photon component to the some frequency and do nothing to the 2 photon component, and that means I could split them by having just a dichroic beam splitter. So a 2-level scatter combined with the some frequency generation step would be a component that splits a 1 and 2 photon components, or 2 photon parts of this beam very efficiently. And then you can do things like Bell state measurements, as Anders was also proposing, but do it very resource efficient in this case. Just 4 of those events, those single 2-level scatterers and some frequency generation steps implemented in a linear optic circuit should be sufficient to do deterministic Bell state measurement. And you can even think about making a nonlinear sine gate, but in order to do that, you really need to store the photon also. You need a quantum memory, because you need to reverse the pulse distortion that you get by scattering. All right, so this is a Lego slide, because summarizing what I think we are doing in this field. So we are building Lego blocks. We're not starting to put the Lego blocks together yet, so my kids were very disappointed. They learned that I do Lego at work, and they were excited. And then when I explained them that we didn't even start to build, they were slightly less excited. So I think we have been constructing these Lego blocks. We have these single photon sources that are very high, very efficient. We can use them as a nonlinearity as well. We know how to improve the performance of them. And then there's really a lot of engineering in order to route the photons very efficiently, because photonic crystals are very, very good for enhancing light-matter interaction, but they're lousy for routing photons. So they're extremely lossy. You can propagate photons over 100 microns typically, then you're limited by fabrication imperfections that leads to Anderson localization, things like that. We have studied that in lots of details. So you want to get out of the photonic crystal waveguides as fast as possible. And this is an impedance matching task, that you're engineering this interface from a photonic crystal structure to dielectric waveguides for doing your photon circuitry. That's really how you don't want to compete with dielectric waveguides for routing or propagating photons, and then you can do your photon circuitry based on standard dielectric waveguides, and the superconducting nanowire detectors also are really coming along that naturally can be integrated on such a platform for highly efficient detection of photons. And of course, you can also start to do more quantum dots, and Edo was also talking about that. There are challenges, obviously, of overcoming inhomogeneous broadening and also doing tuning, and I think Edo pointed that out very well. I think another an additional approach that you can take instead of the position growth, because one of the troubles there is really to what extent you can do that. You can preserve the good optical properties, really the indistinguishability of this 96% that I was talking about. Another approach would really be to optically identify these quantum dots. We can do that with very high precision. You can just optically go in and say there's a quantum dot with 10 nanometer precision relative to a alignment marker. I can find another one, and then I say I want to couple 3. This is my ambition. Well, then I could design a nanostructure that couples exactly those 3. The nanostructure, the engineering potential of the nanostructure is extremely forgiving. That if I'm just solving Maxwell's equations very seriously, I could see that I could couple. I mean, qubit for qubit, quantum dot for quantum dot. I could scale these systems. I think that's the approach that we will be trying. This is not a way of. Then you still need electrical gates or strain tuning to, of course, overcome spectral diffusion. Nice thing of doing optical characterization first is that then you also can cherry pick them and say, okay, I like those 3. They're within a nanometer of each other. This is a way of doing 1, 2, 3, 4, 5. I don't see we can do hundreds, obviously, with a technique like that. But each of those would be deterministically coupled, ideally. So I think that's a resource that we are striving to exploit. That becomes really a realistic resource in this field. I think I'll skip this part, which is about that some of the physics, new physics that is also there in the quantum dot systems, that they might, and they're extended emitters, they don't have rotational symmetry, so that means that dipole approximation actually sometimes breaks down in these systems. And we have observed this and understand this quite well, also microscopically what is going on. So I'll just conclude and say that I've talked about photonic crystals. We can control spontaneous emission, but more generally we enhance the interaction between light and matter, a single photon and single quantum dot. We can have deterministic and highly directional single photon emission by engineering the photonic crystal to do that. I showed some first results on single photon nonlinear optics, and I talked something about these building blocks and architecture for scalable quantum networks that we are pursuing. And I would like to acknowledge the group that you see a picture of here, the Quantum Photonics Group at the Niels Bohr Institute. We're around 15 researchers, and I should acknowledge our collaborator at KIST Korea for growth of quantum dots, and again refer you to this very modern physics paper where we are kind of reviewing the status of this field. Thank you very much for the attention.
Chiral waveguide work, you have to control the position of the quantum dot, right?
Yeah, that's true. But I forgot to mention that the structure here is actually engineered also to have to be spatially robust also. So that's the idea behind the glide plane waveguide, that you see the spatial map here of the directional beta factors. There are many spatial positions that have a high directionality. Even without the glide plane waveguide in a regular photonic crystal waveguide, there are also spatial position where you have a circular polarization, where you will also see this directionality. That's completely true.
Yeah. I had a question when you showed the transmission data and the reduction of
Yeah.
the transmission from the quantum dot. I think I was a little confused because here I thought your claim was in part that the transmission doesn't go down that much because of spectral diffusion.
Yeah.
But then on the next slide, G2 is essentially 1. At long times, which would suggest that there's not really spectral diffusion or fluctuation of spectral diffusion.
Oh, why would that suggest this?
Well, G2 at times near 0 shows you all the fluctuations at all frequencies of the system.
With excess noise. But usually it's a kind of reasonably small spectral diffusion.
Yeah.
With as an excess noise.
Yeah, no, it's not excess noise due to spectral diffusion. This is something this is really the emitter, so it falls off with it.
Not at 0 time, but at like 10 nanoseconds, let's say.
Yeah.
Is the spectral diffusion, if it's slow compared, or if it's fast compared to 10 nanoseconds,
Yeah.
it should show up as a
Yeah.
feature in this graph.
No, it's slow compared to 10 nanoseconds.
Then it should show up as an offset.
Yeah, so that right, so there could be something on a long time scale. Yeah, that's.
So this normalization here is not actually, it is not really absolute normalization.
No, this is to the next pulse, you can say, to the neighbor pulse that comes 13 nanoseconds later.
It's not actually.
You can ask that of every quantum dot talk we've heard. Absolutely. It's just normalized to the nearest neighbor, and you don't know if that's really the force on them.
Maybe it's interesting to see it that way.
No, I think that you should know what does one mean? And it doesn't necessarily mean one.
No.
There are excess fluctuations.
No, but like on the positive
What?
side, this can be used as a probe.
Absolutely.
Yeah.
No,
Yeah.
it's a power, to know what one really means is powerful about what the noise means.
Yes.
Also regarding that transmission measurement, did you try weak above band gap?
This is with weak above band actually to get this performance. So this was actually quite a tour de force just to get this performance. And I think it's clear. I mean, you want gates in these structures too. I mean, you apply a weak above band field to try to passivate some of the surface traps and so on. But this is a dirty game.
I had a question about, so when you say you see 98% emission into the waveguide, can you say more about experimentally how you infer that?
Yeah, sure. I said it very briefly, but so let's see. So you want to measure you measure the rate, the total decay rate. That's this guy here. So that would be you get directly from the rate. The hard part is to get the uncoupled rate here, and that you search for quantum dots that are slow, but they have to sit in the waveguide, and we ensure that to do that by collecting light from the grating. So that's if you're just measuring, it could be sitting outside the waveguide, and it could be sitting in the bandgap reading. So you're looking for the slowest quantum dots that are sitting. That are still coupled to the waveguide. So that means it will have a residual coupling, gamma WG as well. And that's a 0.1 inverse nanoseconds. That's the slowest one that we get. And then you want to make sure that the slow one that you measure, the gamma non-guided rate, is a typical, is a good comparison to the gamma non-guided one that the well-coupled quantum dot has. But and that you can actually from its rate that you measure, you limit down the spatial position that you can sit at, because we have calculated the local density of states in the structure. And this is why we can say it's a lower bound of 98.4%, because we know that kind of an upper bound of this gamma NG, and we also know that there will be some residual gamma WG, because otherwise it wouldn't emit to the grating, we wouldn't collect light from it.
So there's no more questions. Let's thank all the speakers.